Welcome. This will be the first in a series of videos as we begin our study for Math 109, Math for Educators Part 1. So today we're going to begin with our work on Unit 1. We'll focus our energies on problem solving, and we'll be taking a look at several strategies that you might employ as a teacher for youngsters. We'll work our way towards things that are less concrete and a little more abstract as the course evolves. But it's important to remember when we work with youngsters relative to mathematics, most of their solutions are guess and check, a very concrete, hands-on kind of style. And that's what we just have to realize as we move forward. All right, so I'm going to go ahead and share. Hold on tight here, and we got a PowerPoint. We'll see if we can get good things to happen. All right, we got a PowerPoint. Crank it up from the beginning. Okay. Header slide looks like Unit 1's content comes from Chapter 1. On most of the PowerPoints that you'll see in this unit, you'll see good old Dell setting up what's in store for us as we begin the unit. You'll also come to realize that one of my pet peeves as a student has always been, well, somebody will like that slide and then read it to me. I'll let you have the time and freedom to read what's on the slide. But basically, Chapter 1 involves why is it that we have such a struggle getting kids invested in problem solving, and how might we motivate them to be able to take the risk of saying, I think the answer is 4, and then give them the rationale for a way to explain why that answer makes sense. So as Chapter 1 evolves, that's one of the things I'm going to ask you to keep on a brain cell tucked away. What do we do to motivate kids to feel less threatened by the notion of solving math word problems? And how can we motivate them to be a little more free in their ability to say, well, this isn't bad, I can do this, and maybe a little less fearful, a little less anxious of the concepts and the subject in general. All right, more what's in store. We'll take a look at Polya. Polya seems to be the big guy in terms of problem-solving models. I've seen this author uses 4 steps for Polya. I've seen some with 5. But he seems to be the guy. His methods and strategies seem to be parroted by a lot of books. Chapter 1 only has 2 sections for us. So we'll be going to look at possibly ways that we can look at solving problems. And then we'll take a bridge and we'll try to look at some patterns and how the use of patterns can serve as a bridge for us as we get our youngsters headed towards an algebra point of view. Objectives will be included for each of these PowerPoints. Again, I won't take the time to read them for you, but you can certainly refer to them at any point in time. They're also listed on the overview page for each unit. So you can see we got a couple of from 1.1, and we have actually a few more from 1.2. The next slide will bring up a couple of more. We will be looking at sequences, both arithmetic and geometric. I'm going to do a bit more in the PowerPoint set than you actually will find in your author's text. I think he is kind of in this edition phased out the notion of recursive form, but I kind of think it's worth a look. So I'm going to choose to include it because I'm the teacher, and we'll just play it that way. All right, section 1.1. Gonna solve some problems. Here we go. So we'll start right in with Polya. Step 1 says, what's the problem ask me to do? What might I be asked to find? What content do I know? What might help me? What are they asking me to find? I tell kids, even if you've got horrible memories of word problems, you should be able to read the problem and at least know what it is they're asking of you. What are they asking you to come up with? You may not have a clue how to go about ascertaining what that is, but you should at least be able to know this is what I think they're asking me to find. All right, once we've decided what it is that we know and what it is that we're being asked to find, it's important to come up with some kind of a strategy whereby we might be able to solve that problem. Polya says maybe there's a pattern. Maybe we've seen similar problems in the past that we're going to refer back to. Maybe there's an easier problem or a more simple approach we might be able to use as a model. All right, then we're going to come up with some kind of a plan to go ahead and solve this thing. Maybe we'll do a table or a list, maybe some kind of a diagram. Guess and check is big for youngsters. I don't know that we want to discourage them from using it. I do think as kids transition to middle school age, certainly 9th and 10th grade, we want less of a reliance on guess and check, a little bit more of a maybe an algebraic perspective or something a little more abstract in terms of solutions. Generally, for math people, equations basically open it all up. If we can get them to an equation, we have a fighting chance that they can solve that thing and come up with a solution. Step 3, according to Polya, go ahead. Now you've got a plan. Go ahead, implement that plan, and go ahead and see if you can solve it out. Watch out for units. Units have become more significant in terms of importance, in terms of standardized tests. I'm not saying it's good, bad, or ugly. It's just something to be aware of. All right. And step 4 for Polya says, now that you've got an answer, go back and look at it. Does it make sense? Does it correlate to the information that's been given? If the problem says, how old is Frank? And your answer is -4, probably somewhere there's something gone wrong, because you probably don't care much about Frank 4 years before he was born. All right. So again, at the end, is there something we could have done maybe differently that would have made the solution a little cleaner, a little more easy for us? And those are things that we could look back and try to ascertain as we wrap up our Polya model. All right, we've got a series of examples. Here's example number 1. And the strategy that you're going to employ is you're going to look for a pattern. So basically, here's Gauss. Gauss is a famous mathematician and philosopher, and he's credited for this little formula approach. You can envision Gauss as a little munchkin, always having his hand up. I know. And I'm sure the teacher says, look, I'm going to slow this cat down. I'm going to ask him to add the first 100 natural numbers. So you're sitting there thinking, well, he's going to have to bust out his pencil and go crazy. 1 + 2 + 3 + 4, all the way up to +99 + 100. I'm sure the teacher thought this is going to slow this cat down. I'll have his friends and his classmates a chance to maybe come up with some solutions as well. All right, for those of you who say, well, what the heck, I don't understand this number set business. The natural numbers begin at 1. If you want to contrast it, the whole numbers as a set begin with 0. All right, so 0 is in the whole numbers, but it's not in the natural numbers. So the process is, can we come up with a pattern that might enable us to effectively add the first 100 natural numbers? So since I like you guys a lot, I decided I would list some of them out for us. So I started 1, 2, 3, 4, and then I got tired. And went with the old ... bonus points, if you know that's an ellipsis. And then we got 97, 98, 99, and 100. So there are the first 100 numbers, and you and I are going to certainly try our best to add them without doing the painstaking method of actually brute force adding 1 and then 2 and then add the next one on. It would take about a month and a half. So here's what we're going to do. We're going to be observant. We're going to realize if we pair them up, the 1 and the 100, and we added just those two, that's easy for us to do, we would get 101. And those of us who are very perceptive say, oh, baby, Dell, I think that's not the only place where I could pair up a couple of numbers and get 101 as the sum. So if you go ahead and say, well, that was a fun activity, maybe we could do it again. Yeah, why not? Let's do the 2 and the 99, and I'll be darned if you don't add those to get the same sum of 101. So what we soon realize is that if we continue this pairing mechanism, I'll show it again with the 3 and the 98. Oh my gosh, once again, the sum seems to be 101. So we are pairing up individual sets of 2s, and we are coming up what looks like a constant 101 for each of those sums. So we've got something that might enable us to come up with some kind of a method solution to this, rather than having to add all of those numbers by brute force. So the next slide says, let's get creative and let's get smart. All right, so first of all, we have to convince one another that there are, in fact, 100 numbers in that chain of numbers from 1 to 100. And if we do this pair-up approach, you guessed it, my friends, we could generate 50 such pairs. Remember, there were 100 numbers. We're pairing 2 at a shot. That would get us 50 pairs. And we've kind of already realized that the sum of each of those pairs of 2 seems to be 101. So rather than taking the painstaking time and adding all of those digits, our significantly swell approach seems to indicate that if we were to just take 50, which is the number of those pairings, times 101, which is the sum of each of those pairings, it looks like the sum of the first 100 natural numbers would be 5,050. So it's a pretty cool model. We got an answer without having to invest a whole lot of number crunching on our part. All right, second problem. Maybe we have something that we can look back at and use as a related problem as a sketch. Obviously, the most important word here seems to be even. So we won't have all of the numbers that we had on that last slide. In fact, we'll have 2, 4, 6, 8. Again, I got tired, so I chucked that ellipsis in there for us. 94, 96, 98, 100. So if we go back and use that model that we seem to encounter on that first problem and do the pair-up thing, looks like this time the pair-ups are a sum of 102. We add the 2 and the 100. Whole baby, if we add the 4 and the 98, lucky for us, we still get 102. So we are on the same line of logic. pairing things up. Looks like each time the sum coming up at 102. One more time because it's on the screen. Now the kicker is this. We no longer have 100 digits or 100 numbers to be adding. We have, in fact, the evens, which would be exactly half of that 100. So that would be 50 numbers being added. So if we did our pair up trick and we were pairing in groups of 2 and we have 50 numbers up there, you guessed it, my friends, that would be 25 pairs. And it looked like each of those sums of 2 at a shot was 102. So using the same kind of strategy as last time, looks like the sum of those evens would be 25 times 102, 2,550 for those of you keeping score at home. So we used a method, we used a model that we'd invested a look at before, and we were able to modify it in a certain sense and draw the same kind of a solution approach for us. And that, my friends, is the end of video 1 for Unit 1. I'll be back shortly with video 2 for Unit 1. See you then.